Okay, let's consider this then. I've got V standing for volume, but it isn't necessarily a volume in every case. Being the integral from A to B, C to D, f of dy dx. I'm actually integrating in the y direction first, then in the x direction. Now, what does this really mean then? We think about our previous lecture here involving the PowerPoint presentation. Okay, we had what? We had the interval, x interval, being what? From A to B. Okay, and then we had a corresponding partition. So we're creating a Riemann sum for this double integral. Here's our partition. Let's see, it was x sub 0, which is really a, and then we have another x value, okay, x sub 1, which is greater than that, x sub 2 is greater than that, all the way down to, say, x sub m is equal to b, okay? So there's our x interval, and then we have what? We have our y interval, which is what? I think it was from C to D, okay? Here's our partition here in the y. Let's say y sum 0 is c, okay? And then we have a value greater than that, y sub 1, y sub 2, all the way, say, to y sub n is equal to d, okay? Now, I've got the following. Suppose I've got x sub ij, y sub ij, okay? And this does what? This is a sample point in rectangle, rectangle ij. What in the previous video was called r sub ij. That's fine. Okay? What does this really mean here? Well, this is simply saying that x sub ij lies in the ith subinterval of the partition. Let's maybe give this a name, a partition P1, and this is partition P2. It's just saying what? That x sub ij lies in the I subinterval of the partition of the x values, so P sub x or P sub 1. And we've also got this condition, the y sub ij lies in the jth subinterval. Oops. P sub 2. Okay. Alrighty. Now, you're evaluating the function at that sample point. Okay. And then let's see. The length of that subinterval I'll call, of the ith subinterval, I'll call delta x sub I. The length of that r sub ij interval I will call delta y sub j. That's simply what? The length of the j subinterval of P2. Okay? And then we're going to be doing this. Remember, this represents, this is a volume of that thin rectangle that we had in the picture. Okay? And I'll maybe call that I sub j. Okay? Alrighty? And then what are we doing here? We're actually, to get an approximation for V is approximately, what? A double summation here of delta Vij. And we'll talk more about the double summation here in a second. Okay? I hope that makes sense here. All right. Now, with this, when I say V is approximately the double summation, delta V sub ij, okay, I could do this. Well, where is I going from and to? Okay, I could be going from what? What is it? Let's see. I've got 1, 2 to m subintervals. Okay? J is going from 1 to n. Okay? There's what I would be doing. Okay? Or, what's another way of writing this? Couldn't I turn this around? Couldn't I go, well, this is actually the same thing as doing this. Okay? Really wouldn't matter, would it? Okay? Whether you're going to be adding what? In the the y direction first, which is effectively this, then what? In the x direction, or vice versa. You're going to get the same value in either case. Right? We could also write this then, v, let's be a little bit more explicit here. The summation, I goes from 1 to m, j goes from 1 to n. Let's see, that was the function evaluated at x sub I j, y sub I j. You know what I should do here? These look like, I think back in the PowerPoint, these were actually endpoints of the interval. These are just sample points. So let's maybe do this. Let's maybe put like a little bar on top of these or something. Not a bar, it would look like a vector here. Maybe a tilde. Do you know that word? Tilde. Okay. So this is our sample point. I don't know what the PowerPoint had on there, but let's make them little tildes here. Okay, so I'm just saying these are not the endpoints of the subinterval necessarily. Okay. Anyways, this is what we're looking at. Then I have what? Essentially I'm going to write it like this. This is the area of the ith jth subrectangle, right? Okay. Does that make sense? I hope it does. Let's go ahead and consider something real fast here. Okay, I'm going to go ahead and draw on this just a little bit. Do you guys see why I've changed the... I was going to go delta x and then delta y, but I think not. Because you guys notice here what I'm actually doing? I'm adding in the y direction first and completing this on the inside. Okay, and then I'll be doing what? Whatever that result is for each value of I, I'll be doing what? Adding in the x direction. Okay? I hope that makes sense to you. Okay, now I could turn this thing around. Now, I've only got an approximation symbol here. What is the actual volume of this thing? Well, you could think of it as a definition if you want. Okay? This is the actually equal to the limit as the norm of the partition. I'm just going to call that delta. I'm not putting anything on there. Delta goes to 0 of what? Summation like this. I goes from 1 to m. J goes from 1 to n. F of x sub I j tilde, y sub I j tilde. And some people would actually write this, by the way. I should have thrown this in here. Some people would call that delta A sub ij. That'd be the area of the ijth rectangle. Okay, but the way I'm writing it here, I would want y's before x's here. Okay, but I could turn those around here. Now, what is this delta here? This is the norm of the partition. This is the length of the largest subinterval in either partition 1 or partition 2. Okay? So what that effectively means is the length of every single subinterval involved in this situation is going to 0. Now, if this thing actually exists here, then what we have is a definition of the integral from what? X is going from, what was it, A to B. Y is going from C to D. You guys notice I'm integrating in the y direction first, the way I've written it here. F of x, y, dy, dx. This is literally what that means. Now I could change the order of integration here. Okay? we'll see more of this as time goes on.